This lesson is on basic probability, and there are two types of probability in this lesson, theoretical probability and empirical or experimental probability. Theoretical probability is an event that has equally likely outcomes, like tossing a coin, having a boy or a girl, rolling a die, anything like that. And if it's something that happens in theory, so empirical is an event in which the outcome is uncertain or observed, and basically it means that there's an actual experiment being run. In either case, we have these definitions for probability. In the first case, you're taking the favored outcome, possible favored outcomes over the possible total number. And then empirical, you're taking the actual amount of times it occurred over the total outcomes. The set of possible outcomes is called a sample space. Sometimes it can be helpful to draw a tree diagram to list the possible outcomes in the sample space. The subset of a sample space is called an event. So the first example says, list the sample space for tossing a coin. If you're tossing a coin, you're either getting heads or tails. And if you state an event of tossing a coin, you're stating one possibility. So heads, or you could have written tails. If we find the theoretical probability of each, the probability of tossing heads, there's 1 out of 2 outcomes that are heads. The probability of tossing tails, there's still 1 out of 2 outcomes. So the favored outcome is tails, and there's 1 of them, out of the total number, and there's 2 of them. And this is in theory because it's equally likely, there's a 50-50 chance. If you toss a coin in theory, it's a 50-50 chance of heads or tails. Now, if we ran an experiment, it may not be that. I may flip it and never get heads. I might get tails every time. So this is just in theory. Julie wants exactly 2 boys when she has kids. Assuming that having a boy or a girl is equally likely, find the probability of success for each case. In this first part, she only has 2 children. So after 2 children, she's done. We're finding the probability of exactly 2 boys. So if she has 2 children, I could draw a tree diagram. For her first kid, she could have a boy or a girl. For her second kid, after a boy, she could have another boy or a girl. If she had a girl, she could have a boy or a girl for her second kid. So this is boy, boy. I should do, that's misleading. I should do a semicolon. Boy, girl, girl, boy, girl, girl. So this is the order. She had a boy and a boy and a girl and a boy, a girl and a girl. So these are the only possible outcomes that she could have. And that's the sample space. 2 boys, boy, girl, girl, boy, 2 girls. You probably could have done that without a tree diagram. I just wanted to show what that would look like if you did draw that. So the desired outcome is exactly 2 boys. So how many of these represent exactly 2 boys? 1 of them. So the probability of that happening, there's 1 out of 4 total possibilities. So there's a 1/4 chance that she'll get exactly 2 boys. You could write this as a decimal and a percent. There's a 25% chance that she'll get those 2 boys. Now let's say she has 3 children and she still wants exactly 2 boys. Let's draw a tree diagram for that. In her first kid, she could have a boy or a girl. For her second kid, she could have a boy or a girl, a boy or a girl. And then third kid, she could have a boy, girl, boy, girl, boy, girl, boy, girl. Gets a little tedious, but all of these represent an outcome. I think these are colons, not semicolons. I can never remember. So this first outcome is boy, boy, boy. And then boy, boy, girl. Boy, girl, boy. Boy, girl, girl. So that's kind of how that looks. We've got boy, boy, boy. Boy, boy, girl. Boy, girl, boy. This gets very tedious. And then down here, girl, boy, boy. Girl, boy, girl. Goodness. Girl, girl, boy. Girl, girl, girl. That's a tongue twister. So the sample space is this. And I'm just going to write that out. 3 boys, 2 boys, girl, sandwiched, boys, 1 boy. Then 1 girl, sandwiched girls, 2 girls, 3 girls. So our desired outcome is exactly 2 boys. No more, no less. So no, yes. Two boys there. No, 2 boys here. No, no, no. So 3 of them represented what she wants out of a total of 1, 2, 3, 4, 5, 6, 7, 8 possibilities. So there's a 3/8 chance that she would get exactly 2 boys if she had 3 children. 3/8 is 0.375, which is 37.5%. So if we look at these 2 cases here, let me just highlight. She actually has a higher chance of getting 2 boys if she has more kids. So there you go. Okay, here's a standard deck of cards. If you're not familiar with cards, you can Google this and look at images, and there's lots of pictures of this, or you can refer back to this video for the picture. We have this standard deck of cards, that's 52 cards, and we have these different events that we want to happen. So in theory, we're not actually drawing cards. If we're actually drawing cards, that would be empirical. So this is in theory, we have the standard deck, and we're finding the probability of each. So this is the probability of drawing a 2. So let's locate the 2's. How many 2's are there? 1, 2, 3, 4. 4 2's out of 52 total cards. And then you can reduce that to 1/13. Probability of drawing a heart. These are your hearts. There's 2 ways you can look at this. if you look at 1, 2, 3, 4 suits, hearts represent a fourth. Or you can look at the number of cards, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of 52, which reduces to a fourth. So you get a fourth either way. Pause it here, and you find the probability of drawing a face card. That means it has a face on it. And then when you're done, unpause it and see if you got the same thing I got. There are 3, 6, 9, 12 face cards. And then reduce to be 3/13. Which, if you think about it logically, the face cards represent 3 of the 13 different types of cards. I cannot remember the name for that. It's not a suit. Anyway, 3 of the 13 different types. And then the probability of drawing a King of Hearts. So pause it, do it, unpause it, check it with my answer. King of Hearts is 1 card. That's this guy right here. So that's it. And that's that. Last example. Theoretically, 2 dice are rolled and the sum of the dice is recorded. Find the probability of each. So this table represents the number on the die. And then here represents the sum. So pause it, fill out the table, unpause it, and then check your table with mine. 1 plus 1 is 2, 1 plus 2 is 3, 4, 5, 6, 7. 2 plus 1 is 3, 4, 5, 6, 7, 8. 3 plus 1 is 4. You kind of see a pattern here. 8, 9. 4 plus 1 is 5, 6, 7. 6, 7, 8, 9, 10. 7, 8, 9, 10, 11. 8, 9, 10, 11, 12. Okay? And down here it's saying find the probability that the sum is greater than 7. Bigger than 7. Not equal to, bigger than. So pause it, do it, and then unpause it. This represents 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 outcomes are greater than 7 out of a total of, I believe there's 36, 6 by 6. And then you can reduce that. Let me write this over here. 15 over 36 reduces by 3. There you go. Okay, now try this one. The sum is odd. So pause it, do it, unpause it. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 out of 36, which you'll see here, is like, duh, because it's a half. Half of the outcomes are odd. This one, the sum is less than 2. Pause it, do it, unpause it. Are there any numbers less than 2 in this table? Now remember, these are the sides on the dice, so they don't represent a sum. The purple numbers represent sum. Are any of the sums less than 2? No. So there's a 0 chance of that happening. Goodness. And then the last one, the sum is 12. There's only 1 out of the 36 outcomes. That's all I have for basic probability. If you have any questions, please email me or comment below, and I'll get back to you soon. Thank you for watching.